Hello, and welcome back to the math side of Math with Patrick. I have more to share about Stardew Valley and math, and let's get into a few probability concepts using Stardew Valley as our kind of real world scenario. I guess it's a video game scenario, but same thing. So, of course, we're going to talk about some things in Stardew Valley, and there are going to be two main topics for the day. First off, there was a moment in the previous video where there was an interesting drop from an Iridium bat. I think I'll play the clip now. And secondly, I have the burglar's ring equipped. So, for example, with this Iridium bat, we get a lot of stuff just from slaying the one monster. And I want to do a little bit of probability investigation on some of the drops we got. We got some solar essences, we got some Iridium ore, and we got some battery packs. And I specifically want to look at this Iridium ore so that we can talk a little bit more about data distributions. Secondly, I also want to share my thought process behind planting those fall and winter seeds in the greenhouse. I think, for context, let's roll that clip. I'm going to deluxe speed grow some fall forage seeds and winter forage seeds. I'm doing 13 of fall and 11 of winter because I think it's optimal. And just as a backup, I'll do some non-speed grow versions of the same seeds. I just, again, didn't have enough deluxe speed grow. And the whole point of planting those seeds is to satisfy two different bundles in the community center, specifically the fall foraging bundle and the winter foraging bundle. And there's some interesting math happening behind the scenes here too, and we get to talk a little bit more about the inclusion-exclusion principle with probability with the context of these fall forageable and winter forageable seeds. Okay, now that you have the context for what I'm going to talk about in this video, let's get on into the math. So let's talk data distributions in the context of this Iridium bat. And I really only want to talk about the Iridium ore here. We could get into the other items that they drop, but I think the Iridium ore is going to be the most valuable one to talk about when we're discussing data distribution. Now, if you remember the clip, I did get 8 Iridium ore, and here it's saying that you can only get 1 through 4, and we'll get to that part in a sec. But for now, let's just discuss what happens normally when you slay an Iridium bat. They have a specific drop table or loot table, and each of the options for the loot, in this case we're looking at the Iridium ore, has a different percentage chance. From the wiki we can see that an Iridium bat can drop up to 4 Iridium ore, and we do have specific chances. So 4 Iridium ore drops 1% of the time, so almost never. 3 ore drops 15% of the time, 2 ore is 46%, 1 ore is 35%, and then no ore is a 3% chance. So we could take these numbers and make some kind of visualization like one of these graphs to show us a data distribution, and the visualization is just helpful to get a better sense of what these numbers are doing. So I can draw a quick sketch. If you have the space, sometimes it's useful to write the numbers on the bar graph itself. One important concept of a data distribution is that all of the total options need to sum to the number 1. And the idea here is that if we have some kind of probability distribution, we're thinking about what's the chance that any of these events might occur. So if we tally up all of the events, well, surely something is going to occur. So we can do a little bit of addition here with the percentages and just double check that when we add all of these up, we get 100, or I guess 100%, which is the same thing as the number 1. So yes, we have 100% totaled across all 5 of our options, and this is what makes sense in a data distribution. Again, there is a 100% chance that something happens. Okay. Now that we have some kind of understanding about data distributions, let's add some more context from Stardew Valley. One item that I have equipped on my character is called the burglar's ring. That's a lot bigger than I meant it to be. Let me shrink that down. It does just say monsters have a greater chance of dropping loot, but what it actually does behind the scenes is that every time you slay a monster, you get to roll the loot table again. So this is one reason why I might have gotten 8 Iridium ore, because I could have gotten up to 4 from the first roll, and then up to another 4 from the second roll. Let's see what happens to our data distribution now that we have that information. Usually when we have one outcome and then another outcome, and they're both kind of independent of each other, I really like to express these as a grid. So we do have 4 options, I guess technically 5 options. We could get 0 iridium ore from the bat, or 1, or 2, or 3, or 4, and then when we have the burglar's ring equipped, we're going to roll the same loot table a second time. And this 5x5 grid is going to be super useful to show all the different possibilities that might happen behind the scenes, because in game, the loot just kind of spills out from the enemy. So these 2 rolls are independent. And when you do have independent events, you can multiply their probabilities to discover the joint probability. So for example, if we want to know the chance of getting 0 iridium ore, specifically when we have the burglar's ring equipped, we could do the chance for none and then multiply it by the chance for none again. So this would be 3% times 3%. We could also think about it as decimals, 0.03 times 0.03. I think another easier way maybe would be to do it with fractions, because at least this way I can see that the numerators multiply to 9, and then the denominators multiply to whatever this number is, 10,000. And if all of these are percentages, we're always going to have this double 100 in the denominator. And just to kind of concisely save space and not repeat myself, I think what I'll do is just record the numerator in this table, and then just remember that I'm dividing by 10,000 to make it back into an appropriate probability. I just did a few of the multiplication calculations off screen, basically to get, like, say, this number. All I did was take the 46% and then multiply it to itself. Or rather, I did 46 times 46, and then I worried about the whole divide by 100 for the percentages later on. And individually, what this shows is that the most common event is to get 2 iridium ore and then 2 iridium ore again. Hopefully this makes sense, because the most common event for just one roll on the loot table is 2 iridium ore. So if we're only looking at just all the 25 scenarios as being distinct scenarios, of course the most common event is going to be doubling up on what was previously the most common event. However, recall that we don't see these as 2 separate events. Instead, the bat just spills out iridium ore at the end, and we don't know what happened behind the scenes. So here, looking at these diagonals is actually going to be super important, because each of these diagonals holds the same information of how much iridium ore was dropped. Like, for example, this is the only spot where we get 0 iridium ore, but then once we reach this diagonal, both of these distinct scenarios could have been the one to give us exactly 1 iridium ore. So for 1 ore, we need to do this 105 plus 105, which is just going to be 210 out of 10,000. And as you can see, the numbers get a little bit more unwieldy, especially this longest diagonal. We have to add, 5 numbers. But let me do this addition off screen. And instead of approximating this data distribution, I figure it would just be easier to plug in the numbers into Desmos and then get a graph using technology instead of drawing a sketch myself. And it looks similar to the one that I did before, except instead of bars, it's just giving us points. But you can kind of assume, if you really want to, you could put bars around all of these points kind of like this, and it shows basically the same information. Even though the most common individual outcome is 4 iridium ore, the most common overall outcome is 3 iridium ore. Here, though, you can see that 8 is highly improbable, and that's because we don't have the full picture from Stardew Valley. The second and also final game mechanic to bring into this Iridium Bat discussion is the Monster Compendium. This is a book you can read that gives you a special power where monsters have a small chance to drop double loot. The mechanics here are basically that you have a 3% chance to get, it does double the loot. What's different about the Monster Compendium compared to the Burglar's Ring is that the Burglar's Ring gives you 2 rolls or 2 chances to hit the loot table, whereas the Monster Compendium just straight up doubles the loot. And if you saw that clip from earlier, which you did, but let me just play it real quick again with this Iridium bat, we get a lot of stuff. You'll notice that all the drops have an even number attached to them, which gives a lot of evidence that the monster compendium did trigger, because all of the numbers were doubled to even numbers. And real quick, because we got 4 solar essences, we actually know that yes, we have the burglar's ring equipped, because that gives us 1 to 2. And then yes, we have the monster compendium power, because then that would double the result to 2 or 4. So it doesn't mean that the 8 Iridium ore that we got is here on this data distribution. Instead, it's going to be on the next data distribution that we make that includes the possibility of the monster compendium triggering. This previous data table is actually going to be pretty useful. We basically just need 2 of them now though. So let's get one over here, and let's get one over here. But we know that there's a 3% chance of the compendium triggering and a 97% chance of it not. And if it does trigger, our ore count is directly doubled. So instead of 0 through 8, we're gonna get 0 through 16. We are gonna see all the numbers 0 through 8, but then we're not gonna see 9. So in game, it's just gonna be impossible to get 9 Iridium ore from a bat. I think this makes sense because the monster compendium directly doubles the value. So if you're gonna get a high value, it's gonna have been doubled and it's always gonna be even. So our data distribution isn't gonna be kind of a nice smooth curve looking thing. It's gonna have weird bumps and wobbles at the end. Looking at the probability distribution, we can still see that 3 is the most common outcome, even though 4 would be coming from 2 that's doubled sometimes. So it looks like 3 is still more common than 4, even though they're both fairly common already. And then we can see 5 and 6 still happen, 8 kind of does as well, and then all of these really aren't that common at all. And you know what? Let's go on a little adventure. Actually, let's talk about expected value for just a second. I know I didn't mention this at the beginning of the video, but you know what? Let's talk about another math concept. The expected value of an event is basically its average. It's the number that you settle on after a whole bunch of trials. To get that in a probability distribution, you just need to multiply the value times the probability, and then add up all of those different values that you get when you do value times probability. So I kind of automated it with Google Sheets, and I got the value 3.6256. Now, if we just look at our data distribution, this makes sense. 3 and 4 are the most common outcomes. Nothing else really comes close. Maybe this number is greater than 3.5 because we have all of these kind of rare events. So I did get this number by doing all of those multiplication and addition steps, right? Like multiplying the value and the probability and then adding up all of those products. But I think we can verify that this number makes sense by doing easier calculations than trudging through all of these fractions. We could just find the expected value of 1 bat and then double it. This is coming from the burglar's ring. And then finally, with the monster compendium, we need to figure out like what's a good concise number to multiply this by, and I think it's just going to be 1.03. Now the effect says we have a 3% chance to double loot. So I'm imagining, let's say we have 100 bats, and that means that for 3 out of the 100 bats, on average, these 3 would give us double loot. And so we would have, for every 100 bats we slay, we would get the loot of 103. And we can multiply by 1.03 to represent 3% more, or a 3% increase. So the only number that we don't have right now is the expected value of 1 bat, but we can use these numbers from above to get that. So we do have to do a little bit of this multiply, add to reach the expected value, but we don't need to do a table of 16 different entries. We could just do 4. And you know what? This might actually be doable by hand. Sometimes like reaching for calculators when there's way too many calculations, but this actually does seem doable on a human level. And then I do need to remember that these were all fractions, so we still did have this divide by 100 involved. So this shows that for just 1 Iridium bat, no special power-ups, we're going to have an expected value of 1.76. So now we can use that expected value of 1.76, multiply it by 2 for the burglar's ring, and then increase it by 3% from the monster compendium. And at this point, with the decimal multiplication, I would just use a calculator, and it does match with the expected value that I got from earlier using the other method, which was accessing this table and multiplying value by probability and adding up all the entries. Maybe let's bring this number back and make sense of it in Stardew. So Iridium ore is useful because we can make it into Iridium bars. And right now in my run, I sell a lot of Iridium bars. It's basically my main source of income right now. So you can sell an Iridium bar for 1,500 gold. Usually I buy coal from Clint, and that costs 150 gold. And you need 5 Iridium ore to make a bar. So I'm going to divide by 5 to get the rough gold value of getting 1 Iridium ore. We can take the expected value of Iridium ore drops from bats and multiply it by the gold value for every 1 Iridium ore. And we can get, and I'm going to round to a whole number here, we can get a gold expected value from the Iridium ore we get from bats every time we slay one. And I'm seeing 979. So this is a nice conclusion, I think a good stopping point for our talk about data distributions. They're really useful to show just all the outcomes that could happen concisely in one chart. This one in particular has this kind of fun wibbly wobbly ending right here because the monster compendium will only trigger these high ore events when the ore number is even. And now I know that in game, if I come across an Iridium bat, I'm going to get roughly 1,000 gold's worth of stuff, mostly in terms of this Iridium ore when I get their loot. So that is the first half of the video, and this is a nice conclusion. 1 Iridium bat is 1,000 gold. Part 2, completely different. Let's roll that other clip again. I'm going to deluxe speed grow some fall forge seeds and winter forge seeds. I'm doing 13 of fall and 11 of winter because I think it's optimal. So the fall seeds are important because I need to complete the fall foraging bundle, and for the fall seeds, I need, let's see, I already have common mushrooms, but I don't have access to wild plums, hazelnuts, or blackberries, so I do need 3 out of the 4 options here. For the winter foraging bundle, I actually already have winter root and crystal fruit. There's other ways to get them in the game, but I do need to plant these seeds to get the snow yam and the crocus. So there are some interesting questions to ask here. Basically, how many seeds should I plant to be some amount sure that I see at least 1 of a wild plum, hazelnut, blackberry, and then at least 1 of a snow yam and a crocus? So I think the easiest thing to do here is, well, ask an easier question and then build ourselves up to a harder question. What if I really only needed 1 of 4 outcomes from each seed? And let's just think about winter seeds for now. So the idea here is that I don't really know how many crops to plant, but I do want to be fairly sure that I get at least 1, again, say crocus. And all the other ones, the winter root, the crystal fruit, again, pertaining to snow yam, I don't need it. All of those are going to be failures. So basically, we have 4 equal options for each plant to grow into. That's 25% each. And I really want to make sure that I get at least 1 of the plant that I get. Now, I keep saying at least 1 because it would still be successful if I got 2 crocuses and then some other things. We could get super lucky and just get only crocuses, and that would also be fine. I just need the 1 item so that I can put the 1 item in the community center and satisfy the bundle. So when we're working with probability like this, it's a little bit hard to calculate all of these different outcomes where 2 crocuses could be a success, 3 could be a success, all 5 could be a success. There's so many different ways to succeed. There is exactly 1 way, however, to fail, and because there's fewer ways to count that, it's actually easier to calculate this probability by counting up our failures. Basically, what I don't want to see is that I get one of the other 3 plants for all of my different plots. So this is the one and only one outcome that is going to cause me to fail, again assuming that I only need one out of the 4 outcomes of crops. And to calculate this probability, we're going to use the complement rule. I actually discussed this in my previous math video. The idea here is that if we do 1 minus the chance of failure, or the probability of failure, we are going to find the probability of success. And this strategy is useful, again, when there's so many different ways to succeed, it's kind of hard to consider all of them. And to do the math here, the probability of a failure for one given plant is just 3 out of 4, because those are the 3 of the 4 outcomes that I don't want. And then assuming that all of these different crop locations are independent, I could just multiply all of those probabilities of 3 over 4 with each other. And that would give me the compound probability or complex probability of all, say, 5 of these different crops, not giving me the at least 1 crocus I need. So doing 3 over 4 to the power of 5, and then finally doing 1 minus that value is going to give me the probability of success. Now, 5 was just a random number that I drew, so instead of 5, I could put an n right here, which represents the n number of crops that I get, and we could, over on this side, stick some kind of like desired probability, like 95%. We could say, oh, I want a greater than 95% chance to succeed, and then we could solve for this n. So let's think through like our overall plan before we get into the numbers. I want to find the probability that I get at least 1 of, and then I'll just say A, and then also at least 1 of B. I don't know, A is the snow yam, B is the crocus, and then C and D can be the winter root and the crystal fruit that I already have. And whenever we have this at least 1 idea, usually using that complement rule, that 1 minus is super useful. So I can do 1 minus and then the probability of failure. And then we need to investigate a little bit about what this failure means. So I could potentially not see any crocuses. And so let me just write that in. No crocuses. I could also not see any snow yams. No snow yam. However, there is a scenario out there, or there's going to be many scenarios out there, where I actually don't see either. We could just get really unlucky and see no crocuses nor any snow yams. We only see the winter root and the crystal fruit. However, in the calculations, when I do this no crocus idea, and then when I do this no snow yam idea, when I do the numbers there, I'm accidentally going to overlap a little bit of information. And so that's where this picture kind of comes in handy, where you can think that this circle might represent the no crocus scenario, and then this scenario could represent the no snow yam scenario. And if I'm using subtraction to take these out, I'll subtract this amount, and then I'll subtract this amount, and then I've accidentally subtracted this middle amount twice. So the idea of the inclusion-exclusion principle is that we're going to do a lot of this addition and subtraction, and then maybe some addition again. We're going to keep alternating back and forth, because as we subtract out some stuff, we're going to accidentally double subtract out some stuff. So that's what's happening here. If I subtract out no crocus, and I also subtract out no snow yam, I'm accidentally double subtracting out the possibility of just not seeing either, just only getting the other 2 crops. I do want to add back the probability of only getting the winter root and the crystal fruit. So this is my exclusion, and then I'm including another thing back. So let's think numbers. 1 minus, no crocus. That's basically what we said before, just not seeing a crocus over and over and over again. So we get a 3/4 chance of everything else, and then we have n crops to the power of n. Okay, then we subtract no snow yam, another minus 3/4 to the n, and then now we need to add back that possibility of only getting the other 2 crops. And then here I'm just going to do 1/2, because for every single crop, we're looking at basically only wanting these 2 over here. And so that's going to be 2 out of 4, or just 1/2. And then we'll raise that to the power of n for the n number of crops. And this right here, even though it's a little bit weird, is our expression for the probability that I'll need to use for the winter seeds example. I can simplify it just a little bit by kind of combining these two terms together. So I can go 2 times and then 3/4 to the n, and then plus the 1/2 to the power of n. Okay, so we need to think through what this is going to look like for our fall seed scenario, because in this one, I do need at least one of 3 different things instead of at least one of 2 different things. So I am going to go 1 minus and think, actually, let's see, what are they called now? Plum, hazelnut, blackberry. So 1 minus no plum, and then also no hazelnut, and then also no berry. But then I need to add back those kind of overlaps. And so here, since we do have 3 different things, this is actually a perfect time to use this particular Venn diagram. You can imagine this red circle representing getting no plums. This green circle is getting no hazelnuts, and then this purple circle is getting no blackberries. And then the way that we find success is making sure that none of these 3 things happen. And so you can think, actually, we have this universe of all possible crop outcomes, and this is the outcome where we're happy, because we make sure that we aren't in the universe where we see no plums, we aren't in the universe where we see no hazelnuts, and then we aren't in the universe where we see no blackberries. So I'm going to add this one, and this one. Well, rather, I guess I'll subtract them out. But then I do need to add back these overlaps here, here, and here. So let's get that done. So we need to add back the possibility of plum and hazel, and then also plum and blackberry, and then also hazel and blackberry. So let's double check the diagram just to see where we're at. I'll also consider this 1 minus right now. The idea of the whole 1 minus is that 1 represents all possible scenarios, and then I'm subtracting the probability of being in here. So I'm subtracting no plum, no hazel, and no blackberry. And so we have subtracted out all of this stuff in here, all of this stuff in here, all of this stuff in here. So we can see right now that this, and this, these sections are all set, but we accidentally double counted this, and this, and we also accidentally triple counted the center portion. So these parts are accidentally subtracted 1 too many times. So I'll do a -1, -1, -1. And then this middle part is accidentally subtracted 2 too many times. So we did subtract it 3 times, right? Because we had 3 different circles. We do want to eventually subtract it out once. So this is our count right now. We're kind of good in these 3 big sections, and then we need to figure out how to fix up these middle numbers. So that's what the addition does. We're adding back the values of the overlap. So we're adding in all of these. So we go +1, +1. Actually, let me do that better. We go +1, +1, because we add back this whole part. We go +1, +1, because we add back this whole part. And we go +1, and then +1 again in the middle, because we add that part. And so now all of these sections are all good, because we subtracted too much, but then we added it back. And so now these ones are all set, and they're all subtracted just the once. However, in the middle, we have a +1, and we want to get back to this 0. We want to subtract it out just the right amount of times. So the last thing to do is just include 1 more subtraction of the final triple overlap, and that's going to be subtracting out none of plum, hazel, and berry, or equivalently, we could think of this as just being only, what's the last one? Only those common mushrooms. Only mushrooms. There we go. So this is our plan, and then now let's attach some numbers to it. So we have this 1 minus, and then the chance for no plum, no hazel, or no berry, those are all the same type of scenario, where we get the other 3 out of the 4 crops, and so we can do 3/4 to the power of n, because we have n crops. Then, but we do have 3 of these scenarios that all have a similar probability, so we can go 3 times for those 3 distinct scenarios. Next, let's add back those probabilities of not seeing plum and hazel, or not seeing plum and blackberry, or not seeing hazelnut and blackberry. So we'll add back, and then these are those 2 out of 4 to the power of n scenarios, or I guess I could just do 1/2 instead, because we have 2 out of the 4 crops that might be showing up that aren't the ones that we want. And these are 3 distinct scenarios, and they each have the same probability. So I will just go times 3 to represent 1, 2, 3 different scenarios. Now, finally, I need to subtract out the 1 scenario where we have absolutely no plum, hazelnuts, or blackberries, which is the scenario of only getting mushrooms. So for every single plant that we witness, there is that 1 in 4 chance that just every single one happens to be that mushroom. So we will go 1/4 to the power of n. And now we've really built that inclusion-exclusion idea because we have this successive subtracting and adding and subtracting. So now that we have some expressions to use for our winter seeds and our fall seeds, let's actually answer the question of like, how many should I plant to be fairly certain that I'll succeed? And then also, let's figure out if that 13-11 split was the right thing to do. Let's use, say, like 95% as a good benchmark here for a good chance of success. And I think let's actually take a look at all of these 4 functions that I wrote. This first one represents that scenario of we just need at least one of one crop. So this isn't the fall seeds, this isn't the winter seeds. I'm just imagining a scenario where I really only need one of the 4 things to show up. And here the cutoff point is going to be 10, maybe 11 crops to be a little bit more certain, which doesn't bode so well because I only planted 11 of those winter seeds using speed grow. So here's a second function, and interestingly, this has this kind of neat decrease down and then it kind of zips back up. It's a little bit weird that it dips into the negatives because this is a probability. So it is kind of funny that this continuous function that represents a discrete scenario for a little moment has this idea of negative probability. Like if I plant 1/2 crop, there's a negative chance of, I don't know what this is talking about. Anyways, let's go back into the more real world numbers here. Looks like if I plant 13 crops, I have a 95% chance of success. Of course, I only planted 11 winter seeds, so I could go F2 of 11 and see that, okay, I have a 91.6% chance of success. And okay, I know I'm saying success. I did plant those extra backup seeds anyways, so I do have a backup option if my seeds don't happen to grow into the crops I want. But at least for those 11 that are grown more quickly to get those bundles as fast as possible, those winter seeds have a 91.6% chance of success. For the 3 crop scenario, again, interesting wiggles down here. I'm not really sure what's happening there, but I am sure what's happening here. This is telling me if I do want a 95% chance of success, I should plant roughly 14 crops. Whoopsies, I planted 13, so a little bit less than this kind of made up 95% benchmark. We can plug in 13 and see that I have roughly a 93% chance of getting what I want out of that first round of crops. So we have the probability for getting a success out of the fall crops, that's this number right here. And assuming that these events are independent, I can multiply their probabilities. So I could multiply the probability of getting success with my winter seeds. And so overall, I kind of have 85% is pretty likely, but you know, if I did the math earlier, I probably would have done something a bit differently because I don't really like an 85% chance of continuing with my challenge run. I would rather that number be a bit higher. So here's one of the questions I was wondering. Did I do the right thing with this 13 and 11 split? And what we can do here is instead of doing 13 and 11, we can just put a variable in here. Instead of 13, let's call this x. X can represent the number of fall seeds that I planted. And then given that I had a restricted plot of 24 seeds there, because I only had 24 speed grow spots, for this 11, I could do 24 minus x, because this was the 13, and then I had 11 spots left over. These two numbers should add up to 24. So in this middle, the values are higher, and so I'm expecting a more positive outcome if I'm towards the peak right here. I think like this 0 makes sense, because if I plant, say, 2 of the fall seeds, I won't see a success. And then over here, if I plant 23 of the fall seeds, I won't have enough spots for the winter seeds, and I also know I will definitely fail over here. So these two x-intercepts make a lot of sense, because those are the scenarios where I just don't have enough fall seeds or don't have enough winter seeds to even have a remote chance of getting what I want. Anyways, let's look at this peak. This peaks out at, I'm going to round up a little bit, at 13. And that's actually really good because I planted 13 of those fall crops. Although, wait, this isn't the number 13, it's 12.7. So I think I should actually plug in some values real quick to make sure that my claim is true. So let's do like 12 and then 13 and then maybe 14. And okay, yeah, so the probability actually is super close between the 13 and the 12 fall seed scenario. They both round to 85%. 14 would have been overdoing it because, oh no, it only rounds to 84%. So the best scenario is actually planting 13 fall seeds and 11 winter seeds. Again, given my weird restriction of only having 24 crops or 24 spots of deluxe speed grow in which to plant some combination of fall and winter seeds. So something that we could kind of figure out right now is like, if I really wanted that 95% chance of success, maybe I would have needed to up the total number of spots I was farming on. So we could just kind of guess and check until we hit that line. And it looks like we go over the line at 32. And then this curve peaks at 17 and a half. Peaks at 16.7. That was weird. Oh, this was a 17 and a half. So I think it would probably make the most sense if I wanted to get this outcome of a 95% chance of success, that I would want 32 spots that all have this speed grow involved in it. And then I plant 17 of those spots as fall seeds, and then 15 of those spots as those winter seeds. So that's probably what I would have done had I had a little bit of foresight and I wanted to get this 95% chance of success, because that's just a little bit better than 85%. So that's all with the Stardew context. As a little bit of an epilogue, I do want to share, if you notice this inclusion-exclusion principle with these different functions, I even wrote a function for the 4-crop scenario if I actually needed all 4 outcomes. If you glance at these coefficients, we do have the binomial coefficients. It's 1, 3, 3, 1, 1, 4, 6, 4, 1. These numbers come from Pascal's triangle. These come from the choose function. I guess for this one, there is missing a +1 at the end. But if you do consider or continue the fraction pattern, you can see how the numerators of our fractions here keep decreasing by 1. So if we follow the fraction pattern, this would actually be 0 over 4 to the power of x. And this is just the number 0 at the end. So interestingly, we could actually write this in summation notation because each of these terms follows a very predictable format. We have some kind of binomial coefficient at the start, and then we have some kind of exponential product here. So I wrote this absolutely unwieldy summation formula that helps me answer this question when I have n different outcomes from a plant. So kind of extending past the Stardew context, imagine that you plant a seed and it could turn into, 40 different things. And then of those 40 scenarios, you really want to see at least, say, 10 of them. And I generalize this formula, again, using summation notation. Here is my binomial coefficient. This part right here, this -1, considers the fact that our inclusion-exclusion principle alternates with summing and subtracting. And then finally, this is my exponential term, where that numerator counts down as this I value ticks up. The weird part here is, for whatever reason in Desmos, I needed to put this 1/2 here to make this look more continuous. That I'm a little bit iffy about. But I do want to show you, if you had an example where you had 40 random outcomes and you wanted to see at least 10 of them, and let's say we still want that 95% chance of success, just as a random benchmark, we would need what looks like 208.5. So let's say 209 of these random outcomes to guarantee at least 10. So I don't know, I think it's kind of cool that you can generalize this, and maybe this math and this concept would help answer different types of questions. And I did kind of talk about this whole continuous idea here. So what's really weird is that if I type in the right stuff, I can make this curve behave continuously instead of discretely. And it has this kind of interesting behavior. You know, it scrunches up a little bit. And as I decrease this M, look what's happening on that left side there. Again, completely removed from the context of what's happening in Stardew Valley. These negative numbers would represent a negative number of crops planted. Don't know what that means. The values represent a negative probability. Don't know what that means. All of these numbers do make concrete sense when they intersect on integer values of x, but I don't know, the behavior of this thing is just wild. Look at that tail go. Oh, it's just so fun seeing it like wibble wobble back and forth. Yeah, no clue what's happening here. I would love some kind of explanation as to how some kind of discrete scenario, like counting crops, can create such a, I don't know, intriguing, continuous curve deformation here. So that's the little treat at the end of the video, I guess, is this kind of weird scenario of this curve wobbling back and forth. And that's about it. So in conclusion, bats are worth 1,000 gold in Iridium ore. I have an 85% chance of being successful really quickly. Again, I still have those backups, though if I wanted a 95% chance of being successful, I should have planted more crops. And we went over a lot of different math concepts. We had compound events or compound probability. We took a look at data distributions. Specifically, these are probability distributions. We discussed the complement rule, this idea of doing 1 minus the chance of what you don't want. And finally, we use the inclusion-exclusion principle, which is kind of like an application of the complement rule, where we keep swapping back and forth to make sure that we count just the right amount of stuff. And I think that's about it. So thanks for coming along. If you stuck through all this, I really appreciate it. Interact with the video how you see fit. And I'll see you next week back for more gameplay and the next week of summer. Alrighty, bye. I'll see you next time.